Okay, so welcome back to another video. So in today's video we have the following computation that we want to evaluate, and that's infinity factorial. And so I should probably give a little bit of an extension on what factorials are for anybody that's not well versed with that definition. And that says that for any for natural numbers n, so n factorial is defined with n, and then you subtract with each term by 1 and multiply by its product. So we start with n, multiply by n minus 1, then multiply by n minus 2, so on and so forth, until you keep going until you get to the final three terms, 3 times 2 times 1. And some results, if you want to compute these examples specifically, so let's say we have 1 factorial, that's just equal to 1, 2 factorials equal to 2, 3 factorials equal to 3 times 2 times 1, that's 6, and then so on and so forth. 4 factorial is 24, 5 factorial is 120, and so on and so forth, whatever numbers you want to plug in for n. And so that begs the question that asks, so if we have these numbers, so what would infinity factorial be? And a lot of people would make the assumption and say, well, it probably would be undefined because it's just multiplied by 1 times 2 all the way up to infinite numbers, which either you could say it's infinity or undefined. People go with those two answers, but the truth to that is that that's neither of those answers. The result is actually really crazy, and the way to solve this is actually we're going to get pretty much our hands dirty and rewrite a lot of crazy things. This has been something a lot of mathematicians have been coming up from that time long ago on what the finite value of infinity factorial is, and using a bunch of functions that eventually will come in handy as a powerful tool to help solve this this unknown question that everyone might be thinking what exactly that value is. And so with that, let's actually just jump into the video. I don't want to give too much a surprise, like what else, what are the behind the scenes on like what we're gonna on how we're gonna tackle this. So let's start out with the intuition. Say that, so if I'm going to define infinity factorial, we're going to say that we're going to call this capital P. And of course, when we use that definition, that also says that this is 1 times 2 times 3 times 4. Keep going, so far and so forth, all the way to infinity, right? So let's actually take the natural log of both sides. And so we have the natural log of P is equal to the natural log of 1 times 2 times 3 times 4, so on and so forth. And then from here, so what that entails is that you could use the rules of natural logs and write this as a sum of natural logs since the inside the expression forms a product. So this would be, so here we have the natural log of 1, then plus the natural log of 2, plus the natural log of 3, and then you just keep going, so on and so forth, until then you realize that with this you can actually form an infinite sum. And what that comes down to is that sum is the natural log of n. So the infinite sum, natural log of n. Okay, and now with this coming in handy, we will use this later eventually, but let's actually now define a couple definitions. Well, one definition first, and then eventually as we keep going, we'll add in some more to it. So now let's actually define specifically the Riemann zeta function, and that's specifically defined as so Riemann zeta s, and that says that for s is actually the real part of s, since s is a complex number, and that says that this is actually the infinite sum, n is equal to 1 of 1 divided by n to the power s. Now from here, let's actually take the derivative of our Riemann zeta function. This, like I said, we're gonna get our hands dirty here. So once you take the derivative, you can write that as n to the power negative s. So that's actually, the base is a number that's not e, so you use the rule that it's the n to the power negative s multiplied by the natural log of your base, and then multiplied by the derivative of your exponent. So hence being negative s. So once you actually do this, you'll get that this is actually the negative infinite sum, n is equal to 1 of the natural log of n, and then divided by n to the power s. So let me actually underline what we have so far. So, well, specifically for our derivative. So this is what we have for now. So this will come in handy later. So now let's actually plug s is equal to 0 for here. So what that says is that when we plug s is equal to 0, that means we have the Riemann zeta of 0 and then that's equal to, so 0 here, that just becomes 1 on the denominator, and so we just have the negative infinite sum, n is equal to 1 of the natural log of n. Okay, and then also and we can see that eventually we're actually going to make a little claim here and say that this is actually going to equal to negative 1/2 the natural log of 2 times pi. So we have this. So now let's actually prove our little claim over here. And there's a lot going on with this proof here, so just bear with me on this. This is actually, I think, it's very elegant. The result specifically is very elegant, and everything just comes out clean. So let's see. So we have the claim, and that says that we have the Riemann zeta 0 is equal to negative 1/2 the natural log of 2 pi. All right. And so here we start our proof. And so the proof says that we're going to start by using Euler's infinite sine product, and that says that sine of x is equal to x times the infinite product, and is equal to 1 of 1 subtract with x squared, then divided by n squared pi squared. So now let's actually plug in x is equal to pi over 2 for here. So what that means is that, so on the left hand side we plug pi over 2 for x, we get that sine of pi over 2, or sine of pi over 2 is equal to 1. Then we have pi divided by 2, and then now we have our infinite sum over here, and is equal to 1. We plug pi over 2 for in here, so that means simplifying some things out, we get that this is just 1 subtract with 1 divided by 4 n squared. Now, if you actually do a little bit of a simplification over here on the inside expression, meaning like you can get a common denominator from there, pi over 2, then let's see, n is equal to 1 of 4n squared, subtract with 1, and then divided by 4n squared. And now next, what I can do here is that now, what I'm going to do is I'll divide pi divided by 2 to both sides, so the left hand side will be 2 divided by pi, and so we're left with the infinite products expression. But now what I'll do is I'll actually take the inverse of both sides, so now the left hand side will, the reciprocal will flip, and of course that'll still be kept as pi over 2, but now the reciprocal on the right hand side, now we would have that this is just 4n squared divided by 4n squared minus 1. But then in other words, you can actually rewrite the right hand expression of the input as a product of 2 rational functions. The way we can write that as is, so we have the infinite product, n is equal to 1. Then we would have 2n divided by 2n minus 1, then multiply with 2n divided by 2n plus 1. And in case you wouldn't notice, this is actually forms the definition of the Wallace product. Pi divided by 2 is equal to the infinite product of 4n squared divided by 4n squared minus 1. But I'll get to that eventually. So now let's actually write out our little series. Okay, so if we write this out, so we have that pi squared, pi over 2, pi over 2 is actually equal to, so we plug our indexes for each and then multiply through. So we have, this is just 2 over 1 times 2 divided by 3, then times 4 divided by 3 times 4 divided by 5, and then series just keep on, so on and so forth. So now let me just write what we have, and that this is defined as the Wallace product over here. Okay, so now what's next is what I can do is, this will come in handy later, so we can actually disregard this for now, and then we'll come back to it eventually. So now let's actually recall that the polylogarithmic expression, so that's defined as LIS of some complex number z is equal to, so we have the infinite sum, goes from n is equal to 1 of z to the power n divided by n to the power s. So if I were to plug negative 1 for z, so then we would have, so n is equal 1, and then negative 1 to the power n, and then divided by n to the power s. But now, what we can do from here is that, so I'll put it like this. I'll divide a negative 1 to both sides. So this is s of negative 1, and so that's equal to, so if I rewrite the expression over here, so we have to divide negative 1 to both sides, so that means the exponent will have to subtract the 1. So n is equal to 1, and then we have negative 1 to the power n minus 1 divided by n to the power s. Well, what's neat is that by using the relationship with specifically the Riemann zeta function, you can also tell this is also an alternating series with a -1, but because the expansion with that alternating series actually forms what's the nickname known as the alternating zeta function, and if you write out the expression in full, you'll get that this actually equates to specifically this is 1 minus 2 to the power 1 subtract s, and then multiply with the Riemann zeta s. And I'll put down that over here this is known as the this is, in other words, the specific name is also called the Dirichlet eta function. Well, before we get to taking the derivative, there's also another thing I want to do with this series expansion over here before we continue further. Now, I mentioned that we want to take the derivative of both sides, the Dirichlet eta function, this derivative and this derivative. But before we actually continue further, let's actually write this series expansion out a little further. So what we can do from here is we can actually use the Euler transform for this series, and I'll save you guys the work, or if anything you want to verify this with the Euler transform computation, then feel free to prove that as an exercise, you could say. But what that comes down to is that the Riemann zeta, or excuse me, the Dirichlet eta function for this, using the Euler transform here, if we do this, we actually get that this is just 1/2 then plus 1/2 times the infinite sum of -1 to the power n minus 1, and then multiply this with 1 divided by n to the power s, subtract with 1 divided by n plus 1 to the power s. Now I shall also say that this is the condition with the real part of s is strictly greater than -1. So now let's actually take the derivative of our Dirichlet eta function. So when we actually take the derivative of the Dirichlet eta function, we're basically just doing the same method, just like what we did over here when we did took the derivative of the Riemann zeta s. Very similar, because we have a 1 divided by n to the power s where we're differentiating in respect to s. So once you solve all this, so let's see, this will be, so this is negative, if you want to write this, you can write that as n to the power -s, and then subtract with n plus 1 to the power -s. What's nice is that you take the derivative of s, -s, it's -1 for both. So what that means is I can actually factor out a -1 over here, so this will become -1/2. So we have the infinite sum over here. This does not depend on s, so that just stays the way it is, and it's multiplied by a product too, so it's fine. So now that's being multiplied, and now what we have is that this is just the natural log of n divided by n to the power s, then subtract with the natural log of n plus 1 divided by n plus 1 to the power s. And of course, there's a condition that says that for the real part of s is actually strictly greater than -1. So now let's actually plug in s for 0. So that means we have -1, 1/2, then infinite sum again. And now the inside bracket expression, everything for s is 0, so that means both the denominators would be just 1. So we have the natural log of n subtract with the natural log of n plus 1. In other words, you can write that using the rules of natural logs and say that this is just the natural log of n subtract, or n divided by n plus 1, like so. Now from here we can actually expand the series out further. So here we have -1, then this is an alternating series. Okay, so we have, let's see, I'll just write a couple of terms here. So we have the natural log of, so 1/2, then subtract with natural log of 2/3 plus natural log of 3/4, so on and so forth. Well, let's say for over here, this is alternating, this is supposed to be a subtraction. Now from here is, you can actually rewrite this even further. So what I can do is, because there's the natural log, so -1/2 distribute to all the natural log functions. So that means is that that's treated as the exponent. Well, excuse me, we're distributing the -1, not the -1/2. -1 into all of our natural log functions over here. So that corresponds, as using rules of natural laws, that's your exponent. So what that means is you put that back in an expression, that means you're flipping the reciprocal. But really what I can do is that we're only going to flip the natural logs associated with the positive symbol. We're going to flip that reciprocal, and then keep anything with the negative symbol, we'll just change that to the positive. So doing all this, we're going to have 1/2, then multiply with ln of 2 over 1, then plus ln of 2 over 3, then plus ln of 4 over 3, and then you keep going so on and so forth. What's really nice is that, hey, guess what? We just expanded out the Wallace series, and over here we have something very similar, because now we have 1/2, then times the natural log. Keep everything when, so everything is a product of the inside, so this is just 2 over 1 times 2 over 3 times 4 over 3 times so on and so forth. We just use that series expansion for the Wallace product. We can just replace this with pi over 2. So we have 1/2 ln of pi divided by 2. And so that's, okay, so we have this, so that's great. So now let's actually take the derivative of our Dirichlet eta function in relation with the Riemann zeta function. So give me a second to change colors. So now if we take the derivative, so let's see, I'll write this as d over ds of the following here. So this is 1 minus 2 to the power 1 subtract s, then the Dirichlet eta of s. So this is very simple. You actually it's just the product rule. So you take the derivative of this, multiply with this, add this with this, times the derivative of the Riemann zeta s. Show all that work, and then you're going to get that this is 2 to the power 1 minus s, multiply with ln of 2, then multiply with the Riemann zeta of s, okay, and then add this with the Riemann zeta prime of s, multiply with 1 subtract 2 to the power 1 minus s. Okay, so now let's actually plug 0 to here. So plug 0, or s is equal to 0. So we plug s is equal to 0 over here, or how about this? In other words, since this is also the Dirichlet eta function, I'll just write this as the eta prime. And then 0, we plug 0 over here, then we get the following is that this is just, let's see, so we plug 0, so this is 2 times natural log of 2 times Riemann at 0, but that equals -1/2. You can actually show this by using Bernoulli's numbers, which I'm not really going to go over. So that just means this just becomes a negative ln of 2. You plug 0 here, then this is just, so zeta prime is 0, 1 minus 0. Okay, so this will just be -1. Alright, so therefore we have negative ln of 2 subtract with the Riemann zeta prime of 0. Okay, and then we set that equal to 1/2 ln of pi divided by 2, which if you showed the work, keep going forward, that if you just add the natural log of 2 to both sides, then so we have 1/2 natural log of pi over 2 plus ln of 2. So if you would write the 1/2 back into the input, so you get the square root of pi divided by 2, then multiply with the 2 since you're combining the natural log, so it's 2 times that, then put the 2 back into the square root, so there'd be 4 pi divided by 2 under that square root, then divided by 2, and then we have the square root of the natural log of square root 2 pi, or in other words 1/2 the natural log of 2 pi. And of course then you just divide negative to both sides with the Riemann zeta function, so we have that the Riemann zeta of 0 is equal to -1/2 ln of 2 pi, like so. So that actually completes our little proof. So I'll underline, or how about I draw this box in red so we know like this has been complete. So proof. All right, excellent. So we have this. So now let's, we're pretty much almost done here. Now we have the proof complete. So now we can actually just go back to what we said earlier, that Riemann zeta prime of 0 equals our infinite sum. So let me give me some time to write all this out. This is equal to the negative infinite sum of the natural log of n, which we just proved that that's equal to -1/2 the natural log times the natural log of 2 pi. We can actually just divide the negatives to both sides, and so we have now this just positive, the positive infinite sum of the natural log of n, and then this is just positive 1/2 natural log of 2 pi. Okay, but now recall that where we define this infinite sum, we said that this is equal to ln of p, where the whole goal is that we want to solve for p is equal to 1 times 2 times 3 times 4, so on and so forth. In other words, what our given was infinity factorial. So I can just replace p, and we have, well, back with ln of p for our infinite sum. So we have ln of p then equals now 1/2 ln of 2 pi. Then if you just take the e base to both sides, ln of p is equal to e to the 1/2 ln of 2 pi. And if you solve all this out, then so p will just be on its own on the left, and then over here you just move the 1/2 to the input, and then the e and ln's cancel, and so therefore you have that the final answer is equal to 2 pi, like so. And there we have it, the final answer drawn in this black box. Now the answer, of course, it's not equal to undefined or infinity factorial. Instead, it's actually equal to p equals the square root of 2 pi. Now, if you ask me, is that ridiculous? Probably, but you know what? I think that's pretty cool if you ask me.